So our last conic section is hyperbolas, and as you can see at a glance, the equations for hyperbolas look really similar to the equations for ellipses. The only real difference is there's this extra minus sign floating around in the equation. That makes a pretty big difference. And another thing that's different about the actual pictures we get from them is that the direction a hyperbola points, whether it's a horizontal hyperbola or a vertical hyperbola, that's not controlled by whether A is bigger or B is bigger, like it was with ellipses. The thing that controls whether a hyperbola is horizontal or vertical is based on which fraction is positive. If you have the x fraction positive, then your graph goes in the x direction. In other words, the graph is horizontal. On the other hand, if y is the positive fraction, then the graph points in the y direction. In other words, vertical. So that part, that's pretty different than it was with ellipses. One thing that's somewhat similar to ellipses is how you figure out the focus points. Hyperbolas have foci, just like ellipses have foci, just like parabolas have foci. The equation that you use to get the foci is pretty similar to the one we had with ellipses, except, in a sense, it's kind of easier. You don't have to do a subtraction, which means you don't have to worry about setting it up in the right order and paying attention to which one's bigger and making sure you subtract correctly. Here, it's just a squared plus b squared, so you can get it right all the time no matter what a and b are. You'll also notice if you think about the ellipse formulas overall and the hyperbola formulas overall, you'll notice there's always a minus sign somewhere. With hyperbolas, the minus sign is in the actual graphing equation itself, whereas with ellipses, the minus sign showed up here in the focus equation. So overall, at first glance, hyperbolas don't look like they're going to be all that different from ellipses. The equation has a minor modification. The focus equation is really similar. Well, unfortunately, the bad news is that graphing hyperbolas is very different. So let me walk through an example of graphing a hyperbola. And along the way, at first I'm going to be doing some steps that are going to just seem kind of nonsensical. They're going to seem like magic tricks. But it'll come together in the end, I promise. The very, very first steps, though, they're just the same as ellipses. You figure out what A is, and you figure out what B is by the exact same technique. You take square roots. And, in fact, you start out by doing the same drawing process that you do with ellipses. You measure whatever A is, left and right. So in this case, that would be 2 to the left and 2 to the right. And whatever B is, you measure that up and down. So here, where B is 5, we would go 5 up and 5 down. And then, with these 4 dots, well, here's where it gets different. With ellipses, you would just connect the dots and make a little loop. But for hyperbolas, that's not the picture we should be drawing. For hyperbolas, what you have to do, and I know this is going to sound weird, but what you have to do is you have to make a rectangle connecting those 4 dots. And I know you're thinking, why the heck is there a rectangle? That's not at all what a hyperbola is supposed to look like. Hyperbolas are not rectangles. They shouldn't look like this. Well, hold on, and you'll see in a second where this comes together. The other thing that you need to do is take this rectangle and draw the diagonals of the rectangle, the lines that connect the corners, and extend those diagonals out beyond the rectangle itself. And here's where it starts to come together. You're asking, okay, what are those rectangles? What are those diagonals? What are we drawing here? Well, those diagonal lines, those are the edges of the cone that the hyperbola is cut from. Remember, these things are conic sections. They're cut from a cone. So those green dotted lines are the edges of the cone that the blue picture got cut from. So here, imagine a cone, in this case, since we have a horizontal hyperbola, imagine a fairly wide cone pointing to the right and pointing to the left, and then the hyperbola is cut from that. So here's how you complete the picture. Start from the green dots that point in the horizontal direction and draw a curve that looks like a hyperbola that follows those green lines as asymptotes, like this. If it had been a vertical hyperbola, and we'll do an example of one of those in a second, we would have been drawing it up and down. The last step of a problem like this is to draw the focus points. So this part should seem kind of similar to what you do with ellipses, but if anything, maybe a little easier. Here, you're adding, so the order doesn't matter at all. If you mix up A and B, it's not going to make any difference. And just like we've seen when we work with ellipses, it's pretty common to get square roots showing up in here. So, in order to draw the picture right, you should grab your calculator, figure out approximately what square root of 29 is. It's around 5.4. And then draw the focus points where they logically should be. Looking at this picture, seeing how these things curve horizontally to the right and to the left, then we should be drawing our focus points 5 units to the right, 1, 2, 3, 4, 5, 0.4, a little bit more, and 5.4 units to the left, 1, 2, 3, 4, 5, and a little bit more. So you can see from this first example that graphing hyperbolas is much more difficult than graphing ellipses. There's a lot more work involved in this. Another thing about graphing these hyperbola graphs is the first half of the problem might be exactly the same for a different final graph. So let me show you what I'm talking about. Let's take the equation we just did here, and I'm going to make an extremely minor modification. I'm going to take the minus sign that's currently in front of the y squared fraction, and I'm going to move it so it's in front of the x squared fraction instead. Other than that, everything else is identical. So the way you would start this problem is exactly the same way we started the previous one. You would start with figuring out A and figuring out B, which are the same as they were a second ago. So you would go left and right 2. You would go up and down 5, which is exactly the same as it was a second ago. You would draw the exact same rectangle that we drew just a second ago, and the diagonals are even going to come out exactly the same. So for this first half of the work, nothing is different about this problem compared to the previous one. It's all exactly the same results. But then what's different is which direction does this hyperbola point? For this one, the y fraction is positive, so our graph is going to point in the y direction. In other words, this time our graph is going to be vertical, which means we're going to use the vertical points as our vertex points, and then we're going to draw arcs that curve up and follow the asymptotes vertically. So suddenly the process becomes different at that stage. The rectangle's the same, the diagonals are the same, you have the same dots and it lines up to that point, but then you draw a different picture at the end. Another thing that's the same is the value for C comes out exactly the same as it did last time. We're again going to get C equals the square root of 29. So once again, just to remind you, that's about 5.4. But the direction we're going to go is different. We're not going to go left 5.4 and right 5.4. Instead, we're going to go up 5.4 and down 5.4. And we're going to get points just a little bit past the vertex there and there. So you can see you're probably going to have to practice this graphing stuff for hyperbolas. This is a much more involved process. It's going to be harder to remember. And if you don't practice it, you're going to really struggle on the next test. There are some exceptions. There are some hyperbola equations that we do not do this way. So that might sound a little scary, but the good news is they're actually easier to do. So the special case hyperbolas, the equations look really different. You'll never get them confused with this one. They don't look anything at all like these equations. The special case hyperbolas are equations that look like this, where there's either xy equals a positive number or xy equals a negative number. And for graphing these, this is really almost the simplest thing you can possibly imagine. You just make a table of values by thinking of numbers that you multiply together to make 4. So, like, say, 2 and 2, or 1 and 4, or 4 and 1. You should probably try to think a little creatively about this and include things like -2 times -2, or -1 times -4, or -4 times -1. And you might also want to get really creative and think about things like 1/2 times 8, or 8 times 1/2, and so on. So don't just be lazy and do like 2 or 3 examples. Be creative. Come up with several examples of pairs of numbers that you can multiply to make whatever total you're supposed to be making. And then once you've got like good 5, 10, 20 different dots, go and draw those dots. So 2, 2 is there, 1, 4 is there, 4, 1 is here, -2, -2 is there, -1, -4 is that one, -4, -1 is that, 1/2, comma 8 is like there, 8, comma 1/2 is like there, and eventually if you do enough of these dots, you can start to see what type of hyperbola we're talking about. We are talking about a hyperbola where the asymptotes are the x-axis and the y-axis. And for these special cases, the asymptote is always the x-axis and the y-axis, so you never even have to worry about where the asymptotes are. So although these might appear to be more complicated, they're actually easier to draw. Let's do this other one here. xy equals -2. So let's see. What are some pairs of numbers that you can multiply to make -2? Well, 1 times -2 comes to mind, or -1 times +2, or 2 times -1, or -2 times +1. And of course you can try to get creative, throw some fractions in there, like say -4 times 1/2, or 4 times -1/2, and you keep going with these examples until you think you have enough to understand what the picture looks like. And if you've done these like 3 or 4 times before, you don't need to do quite so many until you know what the graph's going to look like. So let's see, let's plot the ones we've got. 1, comma -2 is there. -1, comma +2 is up there. 2, comma -1 is there. -2, comma 1 is there. Let's see, -4, comma 1/2. 4, comma -1/2. Eventually you can start to see, okay, it's a different graph than the other one because it's in a different part of the graphing rectangle. It's to the top left and bottom right instead of top right and bottom left, but it's kind of the same sort of picture overall. So these ones are different than the other graphs that we draw, but they're actually easier, so don't panic. They're actually a kind of a relief compared to the other conic sections we've been doing. And here at the end of chapter 13, where we're not going to be doing any more conic sections, we also pause to do sort of an overview of all the conic sections we've studied so far, circles and parabolas and ellipses and hyperbolas. And you may have noticed that in most of the problems we've done, the more advanced ones, the equation has often started out with everything pushed to one side of the equation and everything all multiplied out. Sometimes even things are put in descending order. So this pattern is often the normal starting place for graphing a conic section, which means that we should probably start with a question of what kind is it? What kind of conic section do we have? And it turns out there's a pretty simple rule you can use to figure out, just looking at the equation without doing any work, you can figure out what type of conic section you're looking at. So, first of all, think back to parabolas. Parabolas were one of the easy ones we started with, and if you think back to the equations we had back there, your typical parabola has an x squared, but it doesn't have a y squared. We did study horizontal parabolas, and horizontal parabolas do have a y squared, but they don't have an x squared. So for parabolas, you will only have either x squared or y squared. Now, when you're looking at this general equation like this that covers all the possible bases, what that would basically mean mathematically is either b is 0, so the y squared term isn't even there, or a is 0 and the x squared term isn't even there. So the rule we can get out of this for parabolas is that if a is 0 or if b is 0, then the shape you're looking at, it's a parabola. Okay, that's a pretty simple rule for parabolas at least. Now let's think about ellipses. Think about all the equations that we saw with ellipses back in 13.2. They did have both x squareds and y squareds. But now that we've also studied hyperbolas, we now realize there could have been minus signs in there when we were doing ellipses, but there weren't. So we didn't notice it at the time, but actually one of the special things about ellipses is the x squared and y squared terms were both positive. It's possible that they could also both be negative, but that's usually dealt with immediately by multiplying through by a -1, but it's at least a possibility that we should consider. So what we're going to say is that instead of saying if a and b are both positive, we'll just say if a and b, if they are the same sign. And that'll allow for the possibility that maybe they're both positive, or maybe they're both negative. So in that case, you would have an ellipse. Ellipses are kind of a modified version of a circle. So a circle kind of actually falls under the ellipse heading. The only thing that really makes it a circle instead of an ellipse is that your horizontal radius and your vertical radius just happen to be exactly the same as each other. So you can think of a circle as just a particularly nice symmetric ellipse. And what that would translate into, in terms of the coefficients for x squared and y squared, they would come out not just the same sign, but they would come out literally the same. So we're going to say if a equals b, just plain equals, then the shape you get is a circle. But that's kind of minor, because that's really sort of just like a special form of an ellipse. And then the last possibility, the one that we just studied here in 13.3, the last possibility is the hyperbola. And that works kind of like the reverse of what happened with an ellipse. A and b have to have opposite signs. So if you're looking at this, and if a and b are opposite signs, then you get a hyperbola. The way I've described the rules here is a fairly practical way to describe them. That's probably how, when you're looking at the equation, how you're going to make your judgment call about which type of conic section it is. But the way I've written it would not really make most mathematicians happy, because in the way I've described it here, there's sort of a sneaky, more efficient mathematical way to describe things. So, if I summarize these in a mathematician's style way of doing things, here's what I could say to make a mathematician happy. I could say, oops, wrong letter, my mistake, I wouldn't say that. That wouldn't make anybody happy. A times b equals 0, or a times b is bigger than 0 or a times b is less than 0. Let's think about it. If a or b are 0 in the parabola case, then when you multiply them, you'll get 0. If a and b are the same sign, that means they're either both positive or they're both negative. When I multiply them, the result will come out bigger than 0. And for the hyperbola case, where they're supposed to be opposite signs, one of them's positive and one of them's negative, if I multiply them, it'll come out negative. So mathematicians like that last way of describing it over there on the right. You don't have to memorize those rules. I mean, they're kind of cute. Maybe you want to memorize them. But if you just want to remember the stuff on the left, a little bit more like rule-based way of thinking about it, that'll get you through the very last thing here in section 13.3.